So we're going to try notes a little differently than last unit because I know a lot of you did not listen to them as you were supposed to. So for this set of notes, I will be handwriting them and talking over them at the same time so that I know that you have enough time to also handwrite them and listen to them at the same time. So I suggest if you need extra time while writing, just pause after each line instead of going through the entire video and then having to go back. I think it will be better if you just go line by line. You can slow down the video if you need to, slow the speed down, or you can pause after each line if you need extra time writing, okay? So these notes are going to go over compounds, and composition. So there are two types of compounds that we'll talk about, and the first one is molecular. These are a chemical compound whose simplest units are molecules, meaning it's made up of molecules, typically 2 molecules. Examples of these are pretty common ones that you are familiar with, like H2O and CO2. So they're a chemical compound whose simplest units are molecules. They're also categorized by the type of bonds that they form, and we'll talk about those later at a different time once we understand compounds and compositions completely. The second type of compounds that we'll talk about are ionic compounds. And like the name suggests, they are formed by ions. And if you remember from our last set of notes, there are 2 types of ions, cations and anions. Now, between these, one of them is positive and one of them is negative. So, which of these is the positive ion? We're going to mark it with a positive right here. The cations are positive, and the anions are negative. And the way I gave you to remember this last time in the notes, if you don't remember or didn't listen, is that, and it's really silly, but it's honestly the best way to remember it, is that onions sound and is almost spelled exactly like anions, and onions can be bad because they make your breath smell. So anions are negative because they sound like onions. And we know that ions are formed by gaining or losing which subatomic particle? They're formed by the gain or loss of electrons. And that's really important to remember. So if it's a positive ion, they lost electrons, meaning that they lost the negative particle, so they became more positive. And if they are a negative ion, that means they gained electrons because they gained more negative particles. An example of an ionic compound is this Al2 SO4 3. So it looks pretty complicated, but we're going to mark it up so that we know what each of these mean. So this number here means that there are 2 aluminum. And this number here means that there are just 4 oxygen. It only applies to the atom it's right next to. And then this one outside of the parentheses applies to that entire ion right there, SO4. So this means there are 3 SO4s. So if we were to count, if I were to ask how many oxygens there were, we would have to either count or it could multiply so that we know there are 4 right here. And there are 3 of this ion, so that we just multiply those numbers together and we can get 12 oxygens. Okay, that's just one of the things we have to know when we work with ionic compounds. And if we were to use our skills from last unit, and I asked you to figure out the charges of each of these just from this formula, I'm going to rewrite it. So remember that we get these subscripts down here from the charges of the other atom or the other ion. So if we look here and we reverse the crisscross method and we take this up here and this over here, we know that this is made up of Al3 because we crisscrossed, and we'll talk about the charges of them in a second. And then we have an SO4, and then we know it's a 2. So in order to find out the charge of it, whether it's a cation or an anion, we can look at our periodic table and just to double check ourselves. So if we go to our handy dandy periodic table, and it should be marked up by now with the charges at the top because we were supposed to do that last unit. And if we find aluminum, we see that it's in group 3A or group 13, and that has a charge of 3+. And then we won't be able to find the charge of SO4 on the periodic table since it's a polyatomic ion and it's made up of many ions. So if you flip over your handy dandy periodic table, you'll see the important polyatomic ion chart. And if you go through and go down to the 2s, you will see SO4, and that is the sulfate molecule, and SO4, and it has a charge of 2 negative. So we double checked ourselves and we were able to figure out what the formula and the charges were for those. And continuing on down, we will talk about formulas. So formulas are probably something we're pretty familiar with by this point, hopefully. But maybe we didn't know that there are 2 types of formulas in chemistry. So the one that you're probably most familiar with is actually the molecular formula. And the molecular formula is the actual number of atoms in molecular compound. So if you want to spell out the words like I am, side note, or if you want to abbreviate the words like I am, that's fine. If you want to spell them out, that's fine. But you should know what these words mean because I am saying the actual word when I'm reading you the notes. So, and an example of a molecular formula that hopefully we are familiar with is C6H12O6. And we remember that this is which type of sugar? This is the molecular formula for glucose. So just from this formula, we know that there are 6 atoms of carbon, 12 of hydrogen, and 6 of oxygen in each glucose molecule. Okay. And then the second type of formula that you might not be familiar with is an empirical formula. And the empirical formula is the lowest whole number ratio of atoms in a compound. Okay, so the lowest whole number ratio of atoms in a compound. So essentially, if we were to use glucose as an example again, if we did some math and found the lowest common denominator, then we'd have, and we reduced it all, we'd have CH2O. That's the empirical formula. And basically, the reason that we use empirical formulas in science and in chemistry especially is that when chemists analyze an unknown substance, so if they just have a substance, they don't know its molecular formula, but they can determine the elements that make it up and how many of each element are in the compound. So they can figure out the ratio, but they can't figure out like how they all fit together if they just have this unknown substance. So that's why the empirical formula is important. And then through further testing, they can figure out the molecular formula. So now we'll move on to the type of ions. Okay, so the first one that we'll talk about is monatomic ions. And if you remember your bio terms, mono means what number? It means 1. So monatomic ions are ions formed by a single atom. For example, monatomic ions can be found in group 1. Those metals lose 1 electron to get 1 plus cations. So if you're looking at your handy dandy periodic table, your group 1 should have a 1 plus at the top because all of the elements in that group tend to lose 1 electron, which makes them less negative, so they have a positive charge, and they are a cation because those are positive. Along the same lines, group 2 metals lose 2 electrons to get a 2 plus cation. So that's where the 2 plus on the top of that column or group comes from, is that they lose 2 electrons, so they get more positive by the power of 2. And then going along, groups 15 through 17 gain a certain number of electrons that should be marked on your periodic table, but they gain electrons to form anions. Because if they're gaining an electron which has a negative charge, they're going to get more negative, and we know anions are the negative ion. So that's monatomic ions. And then we have binary ions, or binary compounds. And if we remember from our bio terms, bi means what? It means 2. So binary compounds are composed of 2 elements. For example, if we have aluminum and we have oxygen. If we look at our handy dandy periodic table, we can see that aluminum is in group 3A, so it has a 3 plus charge. And oxygen is in group 6A, which means that it has a 2 negative charge. And if we do the crisscross method, we can get the compound Al2O3, or O3, oxygen 3. So some rules here. You're always going to write the cation first. And the cation is the positive one. So we did that. And then remember, you're going to take the absolute value of charges as your subscript. So that just means you don't bring down the negative charge, you just bring down the 2. And the reason for that is, so I've been calling all of our compounds just by their formula, so I just say Al2O3, but that can get super tedious and is not the most efficient way. So, of course, there are rules that we can name these by. So this is our next little heading. Nomenclature rules. Nomenclature rules, woo! And remember, nomenclature just means naming system. So it literally just means the naming of compounds if you're given their formula. So the rules are slightly different for different compounds. So we'll talk about molecular first. And molecular compounds, remember, are composed of 2 or more nonmetals. So earlier when I gave you the example of H2O, we know that hydrogen is not a metal and oxygen is not a metal. So boom, it's a molecule. It's the molecular formula. So the first rule we got to follow when we're looking at molecular compounds we have to remove the ending of second element and add the suffix "ide." And we will get plenty of practice with this, so don't worry. Rule 2, the prefixes dictate the number of given elements in a compound. Let me write that better. Compound. So prefixes dictate number of given elements in a compound. But there's a little exception to that rule. If there's only one of the first element drop the prefix. And the third rule we have to be mindful of is if there are two vowels in a row that sound the same once the prefix is added, the extra vowel is removed. An example of this, if there are vowels in a row that sound the same, once the prefix is added, the extra vowel is removed. So let's say we had one oxygen. Using the rules, it would be monoxide. But since there are those two vowels, we get rid of one of them and it becomes just monoxide. So that's all the rules for molecular compounds. But since we have ionic compounds, we also have rules for those. Some of them are the same, but some of them follow different rules. Or we have to add extra rules. So the way that we write them, the element with the smaller group number is usually so if we look at our handy dandy periodic table and we look at the first set of groups, like groups 1, 2, all the way to 12, we notice that they are what? They are typically the metals. And we already said that the metals go first, but this is just a way to, another way to say the same point. That's why they go first, is because their group numbers are smaller. And if they're both happen to be in the same group, if they're both in the same group, the element whose period is greater is first. I don't know that we'll do too many examples of that, but it's always good to have all of our info just in case. And then on the first element, or the first atom listed, you only give the prefix if it contributes more than one atom. So like I said up there with molecular, if it only has one, you don't write mono with it. You only write a prefix if it has more than one. And then the second element is named by a couple of properties, so let's talk about it. The second element is named by these rules. So the prefix comes from, you guessed it, it indicates number of atoms contributed by that element. Second rule we got to follow. Then we add the root name of, that's not how you spell name. The root name of element. And then the ending is "-ide", the suffix "-ide". And then last rule, same one as the molecular. If there are two vowels, the second, or you could just say one of them is dropped. Okay, so let's do some examples of these, and we will do plenty of examples on our papers, but we'll do some examples here so that you really know what you're doing. So the first example is P4O10. So on this, the first element is contributing more than 1. And all the prefixes that we'll need are on page 216. So I highly suggest that you go there, memorize those, write those down, whatever you need to do, so that you can recall that for examples that we do in the future. But if you go and look, the 4 is tetra. So we're going to write that. Tetra is the prefix. And then the name of the first element, so phosphorus. So tetraphosphorus. And then if you look, and find the prefix for 10 is deca. And then the root name of the second element is ox. Basically ox, not oxygen, it's ox. And then we add ide. But decaoxides, those are vowels that are next to each other that can sound similar. So we get rid of the A, so it's just decoxide. And that is your name for P4O10. Let's do another example, one that is different or a little more complicated maybe. So the second example is NH4Cl. So we should know that NH4 is a compound called ammonium. So that whole thing goes together. We wouldn't break the nitrogen and the hydrogens apart because they already form a specific compound. So ammonium, and then we take this second element, add the root name, which would be chlor, and then add ide to it. So this one is just ammonium chloride. And we don't have any prefixes because this is an entire molecule. And then this one is just one, so we don't add mono. We can do one more example before y'all have to do them all on your papers. And this one is FeNO3. Okay. So this one is tricky for a few reasons, but the main one is that Fe is a group B ion, and group B ions are confusing and complicated because they can form multiple ions depending on their charge. So Fe can either form iron 2 or iron 3. And the only way we can figure it out is if we look at this formula and do the crisscross method in reverse. So we know that this 3 is actually the charge for this Fe ion. And then we know that there's an imaginary 1 there, and then that's the charge for the NO3. Okay, so if we're writing this one out, we can look at our handy-dandy polyatomic ion chart on the back of our handy-dandy periodic table, and we can see that Fe3, we write that iron, and then in parentheses we write Roman numeral 3, iron 3, because this charge right here, we know it's a 3. And then if we look at the other side of the polyatomic ion chart, on the left side, we can find NO3, which is called nitrate. And we know that it doesn't have a charge because it tells us on the important polyatomic ion chart. Okay, moving on. There are also certain types of ionic compounds that are acids. Okay, and so there are a few rules for this. If the cation, or the first ion listed, is H, it's probably an acid. Some common exceptions to this are obviously H2O and H2O2. Okay, so acids, the name is based on the anion ending. So if it typically would have an "ide" at the end, and we know it's an acid, you have to add hydro, that's a Y, add hydro to the beginning, drop the ending, and add ic acid. So for example, HCl, we take chlor, we add hydro, and then add ic acid. So it becomes hydrochloric acid. Another ending it could have is "ite." In that case, you would drop the ending and add ose acid. For example, H2SO3 would be so if you look at your periodic or your polyatomic ion chart and look for SO3, you will find it towards the bottom and it'll say sulfite. And so that's how we know, okay, it ends in "ite." So to name it as an acid, we will drop the ending and add ose acid. So this would then become, instead of sulfite, it would be sulfurous acid. And last one, if it ends in 8, if the ion ends in 8, drop the ending and add ic acid. So for example, HNO3, if we look up, we know NO3 is nitrate. So we drop the ending and we get nitric acid. Okay, so that sums up, if we're given a formula, how we're able to find the name. But if we know the rules pretty well, if we're given the name, we can then find the formula. So that's what we're going to look at now. So we can find the formula if given the name, which is pretty handy sometimes. So in molecular compounds, you're going to write the symbol of the first element, if it includes a prefix, write that number as the subscript. Another rule for the next symbol, and then we do not reduce. We don't reduce because it's the molecular formula, and we need to know exactly how many atoms there are for each one. And then the ionic formula. So if we're given an ionic formula, which is typically what we'll be given, you're going to write symbol for cation, because remember they come first. Then you'll follow that up with the symbol for the anion. If the anion ends in 8 or ite, It is polyatomic. So then you can refer to the polyatomic ion chart. To determine subscripts, use the crisscross method. And then reduce to lowest whole number ratio. Okay, so let's do some examples of these. First example, aluminum sulfate. So let's consult our handy dandy polyatomic ion chart. And we know just from our periodic table that aluminum is Al. And aluminum has a charge of 3 plus. And then sulfate, we can look at our polyatomic ion chart and figure out that that is SO4 2 negative. And now we have to do the crisscross method and bring that down here and that down here. So we get Al2, put it in parentheses, SO4 3. And that is what aluminum sulfate is. Next example we'll do is lead 2 phosphate. And looking at our polyatomic ion chart or just our knowledge, we know that lead is Pb, and then because it has the Roman numeral 2, it'll be a 2 plus. And then consulting our handy dandy polyatomic ion chart, we see that phosphate is PO4 3 minus. So then we do the crisscross method. And then we get PB3 parentheses PO4 2. And that is what lead 2 phosphate is. So make sure that you are understanding the examples that I gave you, and make sure you got all the rules written down. So now that you are going to do your naming worksheets, you'll be able to do them, and make sure you understand how to do them. That way when you have your one-on-one with me, you'll be able to walk me through how to either find the formula if given the name, or find the name if given the formula. But that's all for this set of notes for this first portion.